very different and explains matters better than, more directly than the laws of physics. We inhabit, I say, a world of contingencies. That disturbs a lot of people, because many people want to think that we inhabit a world of laws, and laws determine everything. But I would say we are not left orphans. There are tools that we can use to not determine the future and predict the future exactly, but to tell us more or less which directions systems are going in. And those have to do with networks, for example. Where is it, Lucas? There it is. The idea that a network, networks have been very popular lately, but they're always looked at in a mechanical way. This is a mechanical configuration. But that's not the whole story. Okay? Any network represents an amalgamation, a fusion of mechanical constraint and indeterminacy. Think of it. If you're at any one point in a network, you usually cannot go to all the other points directly. Maybe indirectly, but not directly. You're constrained only to going to 2 or 3 others. Okay? However, among those 2 or 3 others, it's indeterminate where the next transfer will appear. And people tend to forget about that indeterminacy. But there are mathematics that you can invoke on ecosystems to tell you, you give me a network, I'll give you back 2 numbers. One number tells me how constrained it is, the other number tells me how flexible and incoherent it is. And living systems require some of both. They require some of both. We tend to think of them as only in terms of the constraints. But things can be so constrained that they become brittle, they become hard, and a perturbation comes and they just fall apart without requisite flexibility. And our data tell us that real ecosystems do approach a boundary between rigid constraint and flexibility. As a matter of fact, the constraint is about 40% and the flexibility is about 60%. Anyway. So, the worldview has been reordered. Organisms are not epiphenomena. They're real causal agents. Each is unique, even microbiota, each is unique, and each can act as a causal agent. Human free will is totally possible. You have about 4 or 5 levels between synaptic firings and higher level thought. And each of those levels involves material and dynamical autocatalytic configurations. Each level involves contingencies. And each of the contingencies have their particular directions and so forth. Therefore, intentionalities also have a place in the spectrum of contingency. That's good for you psychologists and sociologists. Okay? Also, it tells us that physical dynamical theory is sometimes a poor model for economic, social, and political phenomena. Okay, we tend to try to put everything into this box of physics, but the actual dynamics of physics are usually a poor metaphor. He also says, and this is something people don't like, that there are individual and social responsibilities, because there are now directions to these configurations of processes, and each part has a role to play within it, its responsibility, if you will. So that it reinvigorates the idea of responsibility. I won't go into science and belief. I think we're running out of time. I'll just say that the world of contingencies is a brave new world. The laws of physics have not been overturned. They're still there. They're still operating. But a new window has opened. It's a world of enormous possibilities. It's a world of radical uncertainties. But it is not a world without order. It is a world that does allow some room for hope, however. And that's it.
save time.
Oh, I thought it was going to get away.
I have a thinking about where is ecology in your talk?
Yes.
Okay. I see biology.
Yeah.
You discuss many levels, and we're not talking particularly about ecology.
You're
We're
absolutely
talking about
right.
the system perspective on biology.
Yes. You know, I hinted at it with the utricularia example and so forth, but where this really comes from, and I don't have the slide here, but I do have it. I will have it in the lectures tomorrow and the next 2 days. Where it comes from is working with networks of who eats who by how much, and what I discovered was that there's a particular formula for capturing how well organized the network is, so that we can say if there's some pollution that comes and the disorganization decays somewhat, we can quantify that. This is very important if you want to scientifically demonstrate damage to the environment.
Well, you could also apply this measure to the development of an organism.
Absolutely. Yes, you could. Now, the difference being that organisms are almost machines. That's the problem. Okay. See, we can't help it. We're narcissistic. Okay. We tend to think of biology in terms of the organisms. We tend to think of ourselves, etc. And that's why I say that ecology is a propitious theater to look at organization, because it's not as mechanical as the organism. The organism is very fine-tuned, and we do need flexibility, obviously, or we'll die. But the ratio is very different from that in ecology. As I said, in ecology, it's 60% flexibility and 40% constraint. So that ecology allows us to study the dynamics of life without interference from genetics and a lot of the almost mechanical phenomena that we talk about when we speak about the biology of the organism. Now, when you go away into economics or social systems, you get another problem, and that problem is intentionality. Okay, and most scientists don't want to allow intentionality as part of the discussion. So consciousness and intentionality, you don't have to worry about them in ecology. You can just look at organization free from either genetics and strong mechanical behavior or free from intentionality. That's the pathway that I took. But I don't have many ecological examples. You're absolutely right. When I talked about centripetality, I talked about the coral reef, how the coral reef sequesters nutrients within itself. You can look at it negatively. I like to talk about the soil on the island of Iceland. I don't know, Iceland. When Europeans first came to Iceland, there were very thick soils. Okay, but the Europeans cut down the wood for sailing masts, and they let their goats and sheep go out on the island, and pretty soon the soil washed away, so that when the United States was practicing for the moon landing, they went to Iceland and they practiced in Iceland, okay? Because the soil is sort of evidence of the sequestering of nutrients by the entire ecosystem. And if you radically disturb the ecosystem, it bleeds away. It's true. I confess I'm an engineer, and I tend to think in engineering terms, so I'm trying to generalize from the ecosystem to the organism, to the social system, to the economic system, so that when I give you this distilled form, there's hardly any ecology there. I agree.
What kind of role you think that the constraints play in the big transitions in biology, like the unicellularity to multicellularity, or I don't know, societies to superorganisms? What kind of role do you think?
What kind of role does what play?
The constraints.
The constraints play.
Well,
the constraints, remember, are bound up in growth, okay? We don't explicitly talk about them. I can measure constraint without knowing what's causing it. This is something that is foreign to a biologist, but engineers do this all the time. The thermodynamics is an example. We don't know what the individual molecules are doing, but we can measure the very large effects. In biology, we can measure the amount of constraint in a network without knowing exactly why things are flowing in this particular area. We might know a little bit more about social systems as to why they are flowing there. But in any event, the idea is that the constraints are part of this autocatalytic dynamic, okay, that actually channels resources in certain specific ways to facilitate growth. So that's the major role that constraint plays, is to cause growth. Now, oftentimes the constraints are damaged by contingencies, and you go somewhere else. But the major role of constraints in ecosystems and social systems and so forth is to channel resources along autocatalytic pathways. Do you feel that there's maybe, another aspect to constraint that I haven't covered?
I was thinking about closed and open systems, and I guess that the constraints play a role in the way that they change the behavior of the system, and the system becomes more closed.
Yes, you're right. It tends to become more internalized. I put up this cycle with inputs. You're absolutely right. What happens is that the amount that's circulated within grows with respect to how much you have to put in, so that it becomes dominantly internalized. You're absolutely right. And sometimes the external inputs can even decrease, and still the internal cycling will. But there's a limit to that. There's a limit to that because the system is taking all of this in from other systems. It's becoming very brittle. Everything is now being connected in lockstep, obligate fashion. The constraint grows so heavy that it is vulnerable to collapse. Okay? We see this in economic systems. Well, I won't go into that, but economic systems tend to overshoot the proper balance between the financial market and the physical economy, and what we get is this boom and bust cycle. They overdevelop and then crash. No, you're right. You're right that systems do tend to become more and more internalized and internally, endogenously dependent and constrained, yes.
Thanks.
Up to a limit.
Also, you talk about centripetality as the way of growing better through cooperation. But your examples, I don't see very much difference between the example when you change one of components, the B, enter the system because it is more efficient to the performance of the whole process. Well, and it changes from B to D because D is more efficient. But it could change from B to B1, which is a little bit more.
Yes.
So, what's the difference between competition and cooperation?
Well, as I said, competition is derivative of cooperation. Cooperation is primary, competition is secondary. No, you're absolutely right that it doesn't have to be exchanged. It can be guided. You have the entire system essentially guiding changes within one of the components, so that it's guiding the improvement of the component. That's a very legitimate scenario. I would say that the difference between cooperation and competition mostly is hierarchical, mostly, in that your mutualism at one level induces competition at the next. So I would say that's probably the demarcation between the two. But in any scenario, mutualism is always primary. That's according to me.
Otherwise, the system wouldn't exist.
It wouldn't compete. It can't compete. Unless it's drawn, I see centripetality as a basic, fundamental attribute of life. You see these lists of, what does it mean for a system to be alive? You never see centripetality on there. You Google centripetality, you get a few hits from me, and that's all. But I really feel that autocatalytic centripetality is a major factor in the dynamics of life. I have a few economists who agree with me because they see these autocatalytic hookups in economic systems very often, and boom, they make the system
But
run.
the evolution of centripetality, which means a system that is becoming each more time centripetal, how do I say? Each time more centripetal, more growing.
Yeah.
The evolution of this is through competition between different forms of centripetal systems.
Okay, I see where you're going. See, you give a talk to philosophers, they always catch you. No, I would rephrase it. Maybe it's a matter of perspective. I would rephrase it to say that each time you have an increment, it's due to a contingency. Okay, so that. If you want to say the contingencies are competing against one another, okay, but I don't see it very meaningful. If you want to say that there's a competition between one form and a virtual form, you can say that too, but I'm not sure how meaningful that statement is either. In other words, I have trouble in my own mind framing competition on the same level as mutualism.
No, I was just wondering if the evolution of mutualism toward even more connected system is through
competition.
The selection between systems which
Yeah,
are
yeah.
variants
Yes. Yeah.
of this.
Yes,
So,
well, that happens at the next level. Yes, that's absolutely true. And it happens at the next level. And as I say, I think the distinction is hierarchical. That the origin of competition lies at a lower level of mutuality, and it becomes competition at the next level up.
I'd like us to talk a little more about the sentences. We made a small remark on the sentences about the organization of the system networks.
Yes.
And that this could be important to measure the impact of disturbances on the system. I'm very curious about it.
Well, I don't know, without putting formula up here that may, bore everybody to death. Anyway, okay, the idea is that if we have a network where everything is connected with everything else, I would say that this has zero assemblance to it, okay? There's zero constraint. If I'm at any one point, there's no constraints on where flow will go to next, okay? At the other extreme is if there's an obligate transfer. If I'm at any one point, there's one and only one other node that I can go to. So in this, ascendancy is maximal. Okay? In between is the real world. Okay? In between, we have networks where there are some connections, but not all the connections. And the measure A comes from information theory. Actually, it's called mutual information. And I could put the formula on the board. I don't know. It probably wouldn't be too interesting to everybody. But the idea is that where are you between 0 and the maximum? You can You can take the network. I work with what are called weighted digraphs. Digraphs meaning directed graphs. Okay, the links all have arrows. They're directed, and they have weights. Okay, usually the weight is how much carbon goes from Minidae, a small fish, to striped bass, a big fish, so that there are numbers on them. Okay? I can take this information and tell you where you are between these two, so that if, say, we're right here, and there's a perturbation and it falls back to here, well, there's been a problem. Now, when I first started all of this, I always thought that ecosystems would increase in ascendancy and would maximize their ascendancy. That seems like a logical way to go. That's not what the data told me. Okay? The data told me something extremely surprising. If this is 0, and suppose I normalize my ascendancy by some normalizing factor, happens to be the diversity of the flows, the Shannon-Wiener index of the various flows, you can normalize it between 0 and 1. And if I look at the ascendancy of, some 20 or so networks that I have, what I discover is that they're all grouped right around 0.4. And this represents a balance. Systems with insufficient ascendancy will tend to increase. I plot it. If this is A is equal to the ascendancy over that normalizing factor from 0 to 1, and then I plot up here E equals minus A logarithm of A, what I discover is that everything tends to plot out just a little bit to the right of the maximum of this particular function, which some of you will recognize as the Boltzmann function or Claude Shannon's definition of information. They plot out right here. What that's telling me is that if a situation is down here, if a system is down here, there are many possibilities for new autocatalytic loops to occur. And as those loops occur, the system climbs the hill. If they're over here, they become vulnerable to a perturbation which will come and reset them back here somewhere. Okay? So that the systems that are overdeveloped tend to collapse of their own. And I can even show you by means of a little numerical example how if you start here, things tend to climb up here, but if you get over here and suddenly collapse, it comes way down here, which is what should happen when you have an economic collapse and so forth. So the bottom line is that while I thought originally that ecosystems would progress towards higher and higher ascendancy, apparently it's not the case. Various ecosystems from different habitats, different states of maturity, they all tend to cluster very closely to this maximum, which hasn't been fully explained. It's a phenomenological result. Okay, and this is where phenomenology provides feed for theory. Okay, and now it's your turn as a biologist to come and explain why everything clusters around A equals 0.4.
Well, we need to move to the next topic, but I'll just say one sentence to discuss over dinner. Ascendancy 1 would be not flexible enough to survive in a world of disturbances.
The word of disturbance.
In a world where there are many disturbances, maximum ascendancy would not be flexible enough.
Not at all.
That's how I explain it.
Yeah.
But we discussed this over dinner.
Yeah.
And we need to change to John's talk. Deixa eu dizer a vocês que a gente vai mudar um pouco, porque